Let's continue to part 2 of this chapter, Introduction to Signals and Systems. There are several types of signals. I've arranged them in so-called pairs, and I'll try to explain each one of them. And for some of the types of signals, I have prepared some short videos for you to listen to and watch. I hope the videos will help you to understand. Continuous time and discrete time signals. Continuous time signals are signals that are specified for every real value of the independent time. The variable time is continuous, which means for all values of time. It exists for all values of time. On the other hand, a discrete time signal are signals that exist or specified only for discrete values of time, usually generated by sampling. It has values at equally spaced intervals along the time axis. So if it's continuous time signal, amplitude exists for all values of time. For discrete time signals, the amplitude the signal has amplitudes only at discrete values of time. Analog and digital signals differ in terms of their amplitude. Analog signals have amplitudes that can take on any value in a continuous range. It can be both continuous time and discrete time. If you look at this example, the values along the x-axis are continuous. In this example, is continuous shown here, and the amplitude takes on any values along the vertical axis. Now, for digital signals, signals whose amplitude can take only a finite number of values. A digital signal whose amplitude can take only m different values are said to be m-array signals. Binary signals are special cases for the value of m equals to 2. Binary signals have values of 0 and 1, 2 signals, for example. Okay, now if you see here, if you compare between analog and digital signals, both of them can exist at all values of time or discrete values of time. But the difference is that for analog, the values of along the y-axis have continuous range, but for digital signals along the y-axis, it takes only certain values, certain finite values. Okay, analog corresponds to a continuous y-axis, while digital corresponds to a discrete y-axis. If I can summarize the 4 types of signals we've seen so far, the analog and digital refers to the amplitude of the signal. Continuous and discrete refers to when the signal exists or where the signal exists along the time axis. So when we're naming a signal, we always describe the amplitude first. Analog, digital, right? Then only we describe how it exists along the time axis. Either it's continuous or discrete. Okay, that's why we have analog continuous time, digital continuous time, or analog discrete time, or digital discrete time. Yeah, so if you see here, analog continuous time, it means that the amplitude is analog, which means exists for all range of the vertical axis. Continuous time means the signal exists for all values of time. And then digital continuous time, but the amplitude is digitized. Analog discrete time, amplitude is analog, but it exists in discrete time along the time axis. And digital discrete time, digitized and discrete time. Okay. Periodic and aperiodic signal. A signal ft is said to be periodic if it repeats itself after a regular time interval. So where T0 is the fundamental period, it is the smallest value of time interval that satisfies the periodicity condition. A periodic signal remains unchanged when time shifted by integer multiples of the period, and a signal that is not periodic is said to be a periodic signal. Causal and non-causal signals. Causal signals are signals that are zero for all negative time. Causal signals have zero amplitude, or it does not exist for time less than zero. Anti-causal signals are zero for all positive time. Anti-causal signals are the opposite of causal signals. Non-causal signals are signals that have non-zero values in both positive and negative time. In this course, we deal with causal signals, which means that signals that have values, that have amplitudes, that have non-causal amplitudes for time bigger than zero, and the amplitudes are zero for time less than zero. Even and odd signals, okay, a function or a signal is said to be even if you find that xt is equal to x minus t. Okay, this is an example. If you find the x minus t of this signal, you find that it looks exactly like this. The x minus t of the signal looks exactly as the original signal. Then we say that the function or the signal is an even function. And the function is odd if xt is equals to the minus x of minus t. So if we have this function or this signal, if you take the minus of x minus t, you'll find that it looks the same as the original signal. So if you find that, then it's a odd function. Okay, and please watch the video. I've explained a little bit detail on the even and odd signals. Signals are composed of the even and odd components. A signal ft is equals to the even components plus the odd components, where the even components is given by 1 over 2 of ft plus f minus t, and the odd component of a signal is 1 over 2 ft minus f minus t. So if you want to find the even components of a signal, you apply this formula, and if you want to find the odd component of a signal, you apply this formula. So you can watch the video where I explain the even and odd components of a signal with an example in the video. Okay? Please watch the video where I've shown how to find and sketch the even and odd components of this signal. Odd and even functions have several properties, and the properties are in line with mathematical formulation. If you have an even function, you multiply it with an odd function, you'll get an odd function. If you have an odd function multiplied with an odd function, you'll get an even function. And an even function, if you multiply it with an even function, you'll get an even function. Deterministic and probabilistic signals. Deterministic signals are signals whose physical description is known completely. Each value of the signal is fixed and can be determined by a mathematical expression, rule, or table. The future values of the signal can be calculated from past values with complete confidence, which means that there is no uncertainty about its amplitude values. Some examples are, okay, an example is signals which are defined through a mathematical function or graph. Yeah, it's deterministic. You have a formula for it. Of course, that means that if you have a formula, then you're giving a physical description of the signal, so it is a deterministic signal. Probabilistic signal or random signals is the opposite. The amplitudes cannot be predicted precisely, but only known in terms of probabilistic descriptors. The future values of a random signal cannot be guaranteed, cannot be accurately predicted, and can only be guessed based on the average of sets of signals. They are we can these signals, there's this what the term called a stochastic process, and these signals can be realized only based on stochastic processes, which means it is being modeled by stochastic processes. Yeah. Examples of this type of signals, EEG, evocated potentials, and noise in CCD captured devices for digital cameras, for example. Yeah, finite length and infinite length signals. A finite length signal is non-zero over finite time. Yeah, finite length signal is non-zero over a finite time. An infinite length signal is non-zero over an infinite time. Okay, it's simple as that. And we have an example of an infinite length signal, which is a sinusoid. Yeah. When we talk about signals, we often ask ourselves, how do we measure a signal? How do we know the size of a signal? One way of measuring the size of a signal is by finding the energy of the signals. For real signals ft, the energy can be expressed by this equation. It is taking the integration from minus infinity towards infinity of f squared. If you look at this expression, it is finding the area under the graph of the signal. Okay, so we measure the size of a signal by finding the area under the graph of the signal. Now, if we want to measure the area under the graph of a signal, if the signal as time approaches infinity and the amplitude of the signal goes towards infinity, then we cannot find the area under the graph. We can only find the area under the graph if the amplitude of the signals approaches zero as time approaches infinity. So that means that we can use the calculation of energy as a measurement of size of signals for signals that have amplitudes that approach zero as time approaches infinity. So for signals that cannot be measured by using the energy equation, then we can use the time average of the square of the signal amplitude, which is the power of the signal. And we use this measurement of power as a measurement of the size of the signal. Okay, then that brings us to the energy and power signals. Now, if we try to measure the size of the signals by applying the energy formula or the energy expression which I showed you just now, and we find that the signal or the function has finite values, finite energy values, then we call the signal to be an energy signal. We categorize it as an energy signal. Okay, in this case, then, okay, the necessary condition for a signal to be of energy type is that the amplitude of the signal goes to zero as time approaches infinity, which I have explained to you in the previous slide. Yeah. So if the signal cannot be measured by using the energy expression, and then we use the power expression, then we find finite and non-zero power values, then that signal is called or categorized as a power signal. Now, in this case, okay, if it's a power signal, that means we are able to find the mean of the signal over an infinite time interval. Yeah? So in this case, it means that the signal or the function is periodic or it has some statistical regularity. Yeah. If you can find average over an infinite time interval, that means the signal is periodic, and so that means this signal is a power signal. Okay, so a power signal has infinite energy, Yeah, as I've explained. Okay, if the signal is of infinite energy, then it is a power signal, and energy signals has zero power, right? Okay. Now, for any signal, it can be either energy or power signals, either one. But there exist signals that are neither power nor energy signals. There cannot be any signal that are energy and power signals. Okay, signals can be either one. Okay, either energy or power signals. It cannot be both. But there are signals that are neither power nor energy signals. An example is the ramp function. Okay, in real life, it is impossible to generate a true power signal because such a signal has infinite duration and infinite energy. Yeah. Because of periodic repetition, periodic signals, for which the area under f squared over one period is finite power signal. Okay, that means that if we have a periodic signals, they are categorized. They can be categorized as power signals, but not all power signals are periodic.